we're going to start with trig identities. We're going to be basically working through these identities. This is the last unit of this semester, but it's a long unit. We're going to split it into two kind of two sections. So we'll have a test over both sections, but this will take us to this unit 4 will take us to the end of the semester. Okay. So we're practicing with these identities and these properties, and we won't have a quiz until next Thursday. Okay, so we need a lot of time to get that practice in before we're ready for a quiz. Okay, so let's start off with our notes. Okay, so what is an identity? Identity is an equality which is true for every value of the variable and typical variables are x or theta. Reciprocal identities, these are ones that you all recognize. Sine and cosecant are reciprocals of each other. Cosine and secant are reciprocals of each other. And then tangent and cotangent. Okay, so example A here, given cosine of x, cosine is the ratio for cosine of x is 4/5. Secant of x must be what? Yeah, sorry, put theta. So if we know a trig function has a ratio, then we know the reciprocal is just flipping that value around. Part B, same thing. Okay, now we can actually reduce this a little bit because root 8 is same thing as 2 root 2. I can reduce the fraction and also rationalize the denominator. I want to bring that root 2 to the top. I can multiply top and bottom by root 2. And I can further reduce because the 2's can cancel out.
It's like a previous unit.
Yeah, we're going to use a lot of information from previous unit. Yeah. Kind of building on that. Okay, tangent is negative 1/4, cotangent is just what? If tangent is negative 1/4 and cotangent is -4. Yeah. Quotient identities, these are very useful because we're going to, the idea is that any trig function I can always rewrite as sine and cosine. And that goes with not only cosecant and secant, but also tangent and cotangent. So we can think of tangent of theta as sine over cosine. I mean, we can think of tangent as 1 over cotangent, but we can also think of tangent as sine over cosine. This is going to be really helpful. The other one is cotangent. All right. If tangent is sine over cosine, then cotangent can be written as what? Yeah, just cosine over sine, right? Because we know that tangent and cotangent are reciprocal. So if I have a fraction version of tangent, then I can just flip that. I use this quite a bit, so it's nice to have that. Okay, Pythagorean identities. Okay, so these come from the fact of Pythagorean theorem. Right, if I have a triangle, right triangle, I can do a squared plus b squared equals c squared. So let's look at this one here. Let's say I have a triangle. The angle close to the origin is theta. And let's say we're dealing with the unit circle here. So let's say the hypotenuse is 1. We know the x-axis corresponds to cosine, right? Because cosine of theta is just x over 1. So we can think of this as basically cosine of theta. Cosine theta equals x. So think of the horizontal as the x, the adjacent of my hypotenuse, and then which means the vertical is y over 1, opposite over 1, which is sine. So if I go through Pythagorean theorem, I have a right triangle here. I have cosine of theta squared plus sine of theta squared is equal to 1 squared. And this is going to be an identity that we're going to use quite a bit. Typically, we write the sign first, but it doesn't really matter. And then we put that exponent in between the cosine and theta so that we don't have to use the parentheses. So this is kind of like a shorthand way of writing it. Sine squared theta. I just rearranged it because this is typically what's more common in terms of whenever they refer to Pythagorean identity, they say sine squared plus cosine squared equals 1. But understand that the squared here is the same thing as the squared around the sine theta, but they write it this way so they don't have to use as many parentheses. But we're not squaring the sine and not the theta. That's not what it means. That it means that we're squaring the entire expression. Okay, there's 3 of them. This is one trig identity. Okay, there's 2 more. And let me show you how to get to those other 2 without having to memorize it. So here's how we can build the second one. Okay, so you start off with your original Pythagorean identity. And we're going to choose either sine squared or cosine squared. So let's just do one. Let's do the first one where we're dividing everything by sine squared. So we're going to be able to arrive at the second trig identity simply by just going through this process. All right, if I divide everything through by, yes, question. The one is squared, but we can just leave that out. But yeah, technically, yes, we are squaring every term. Now, I'm going to divide everything by sine squared. And what's going to happen is we're going to be able to arrive at the second identity. And I want to show you this process so that if you memorize this first one, you can arrive at the other two and three without feeling like you have to memorize it. But as long as you know your reciprocal identities, you should be good. Okay, so let's just kind of reduce this process here. What's sine squared divided by sine squared? That's 1. Okay. What's cosine squared divided by sine squared? Cotangent squared. And what's 1 over sine squared? Cosecant squared. Okay, so it looks more complicated to memorize, but I just want to remind you that you don't have to memorize this. You just have to know how to arrive at this one.
Yeah, it's like one in the number two.
Yep, that's right. This is the first one. Here's the second one, and we're going to discover the third one. So what do you think we can do to get to the third one? Divide by cosine squared. Yeah, question. So if we look up at our quotient identity, cotangent theta, same thing as cosine over sine, which is the reciprocal of sine over cosine. Sine over cosine is tangent. Okay, so like you said, for the third one, we can just take our original identity, divide everything by cosine squared, and we should be able to arrive at the other one that we're missing. Okay, so let's see if we can get that cleaned up. What's sine squared over cosine squared? Okay, what's cosine squared over cosine squared? And what's 1 over cosine squared? Secant squared. That's the third one here. I'll put a 3 next to it. So we have 3 trig identities that we're going to be practicing and using today. Okay, example 1. Use Pythagorean theorem. Given that cosine of x is 3/4, find sine of x. So let's build our triangle. We know if cosine of x equals 3/4, we can use SOHCAHTOA to fill out the sides, right? Cosine is adjacent over hypotenuse. Right? What can I use to find my, yeah, a squared plus b squared equals c squared. Careful though that we don't want to say 3 squared plus 4 squared equals c squared, right? Because that 4 is in the hypotenuse spot. So it's not going to be as clean as a 3, 4, 5 triangle. Okay. Subtract 9 from both sides. 16 minus 9 is 7. B is equal to what? Square root of 7. Okay, so now that we have our triangle filled out, what is sine of x going to be? Yeah, opposite over hypotenuse. Okay, we can also arrive at the same solution using Pythagorean identity. So again, we're starting off with cosine of x equals 3/4. We're trying to find sine of x. Well, we have a Pythagorean identity right above us here. So I'm going to write that down here. Now, I'm going to bring that exponent out using parentheses so that we can kind of see where that 3/4 is going to go. Again, this is the shorthand way of writing it, but we understand that that squared really just means I'm squaring the entire trig function. But visually, I think it's going to be more helpful if we do it, if we write it out this way.
Wait, Mr. Yang? Why is it equals 1? I thought it was the hypotenuse squared.
It is, and the Pythagorean identity is coming from the fact that we're dealing with a unit circle, so your hypotenuse is always going to be 1. And I am squaring that 1, okay? And what's 1 squared equal to?
But the triangle we're using, the hypotenuse wants something.
Yeah, so we are going through two different methods. One is going through Pythagorean theorem, where we're building the triangle from scratch, and we put a 3 and 4. But now we want to arrive at the same answer, but we're going to start with this identity.
So it's always going to equal 1. Every identity.
Yes, yeah. If it's a Pythagorean identity, then that means it's referring to this equation right here.
Okay.
Yeah. So we're not building this from this triangle. We're taking it from this known identity that we're going to be using over and over again. Okay, so yeah, so we can cover up part A because we're not looking at anything for part A. We're just going from example directly to part B. Okay. So that's all we're looking at there. What substitution can I make? Yeah, put in 3/4 in for cosine. And that should allow us to solve for sine. I mean, we've got to deal with the squared, but we should be able to solve for sine of x algebraically. So okay, so we use our calculator. What does 3/4 squared become? Down over 16. What can we do with that? Yeah, let's just move that over to the other side, combine like terms, get that sine x squared by itself, and then we can worry about what to do after that. Okay, what's 1 minus 9 over 16? And then to get from sine squared down to sine, we can take the, not the inverse. How do we undo the squared? Square root, yeah. So root 7 over 16, the same thing as root 7 over root 16, which is root 7 over. Just want to show that we can arrive at the same solution. Kind of getting introduced to Pythagorean identity here. Okay, so let's go to page 3. Okay, simplifying. So these are types of problems that we're going to be dealing with here. Simplifying, which is writing in simplest terms. Verifying, which is show why the identity is true by working from one side to the other. We're going to get to this, if not tomorrow, then Friday. And then evaluating is using trig identities to actually solve. All right. So here's some strategies for simplifying and verifying trig identities. So the first strategy is use the correct identity. So if we can get everything in terms of sine and cosine, usually that's a good way of kind of cleaning up. And if you see tangent or cotangent, then think about quotient identity. The nice thing about quotient identity is you can rewrite tangent in terms of sine and cosine. So if everything's in terms of sine and cosine, you have a lot easier time kind of matching, pairing, and reducing. So for instance, if I asked you to reduce that sine of x times cotangent of x, we can rewrite this cotangent in a different form, which will allow us to merge things a little bit cleaner. What can I represent cotangent of x as? So I'm just taking that cotangent, rewriting it in a form that is a little bit easier to match and pair up with that sine. So now that I have sine of x times cosine over sine, what can I do to reduce? What do you see? Yeah, I have a sine x in the numerator. I also have a sine x in the denominator. So what can I do? Cancel out, right? They're being multiplied. So if you want to think of this sine x over 1, you can, and just know that, oh, if I have two expressions above each other and there's no addition or subtraction that's getting in the way, then they're free to just cancel out, which leaves me with just what? Sine x. Okay? So that's just a strategy when you're reducing. Sometimes you look for opportunities to rewrite your expression in terms of sine and cosine. If you see a trig function in the denominator, sometimes it's helpful to bring it up as the reciprocal identity. So what's 1 over cotangent squared the same thing as tangent squared? And sometimes that can kind of help us move to the next step in terms of, oh, okay, there's something else that I can. But right now we're just talking about some strategies that we can use in more extended problems. If we see squares, think Pythagorean identity, so we can look at some of that a little bit later. The next is using algebra, okay? Do you see multiple fractions? Or do you see some denominator that we can put together? So here, if I want to try to, I see cosecant, secant, cotangent, these are all different trig functions. It's hard to see that relationship, but one thing that I can do is, what if I get this so that I can make them more similar to each other, right? So what if I can get everything from the sine and cosine, then I have an easier time kind of merging and putting together. So what can I do with that cosecant? Cosecant is the same thing as what? 1 over sine, okay. All right, secant is same thing as 1 over cosine minus cotangent is same thing as cosine over sine, right? So I mean, we could say 1 over tangent, but our goal, we'll have an easier time kind of seeing the relationship if we can get everything in terms of sine and cosine. Okay, so I'm gonna use the space here because there's more that we can do. Even though we have everything in terms of sine and cosine, we still have two separate fractions. Maybe we can try to get it cleaned up by getting it into the same fraction. So if I want to merge two fractions into one fraction, what needs to happen? I need to have a what? Same denominator, right? So we need to find a common denominator that is large enough for both of these to multiply or to multiply into. Okay. So what's the common denominator that both my denominators can go into? Sine x, cosine x, right? I need both, right? If I just pick sine of x, that's too small for this to go into. But if I pick sine x, cosine x, then that will allow for both to go in, to be a part of. Okay, are we good with common denominator there? Okay, so now we got to balance our fractions, right? Our numerator needs to be balanced. So we ask ourselves, do we see any changes from this denominator to this denominator? No, so that means there's no adjustments needed. I can bring that numerator down. Okay. Do I see any difference between this old denominator and this denominator? Okay, what's been added, right? I've added a cosine, so I need to do the same thing to the top. I need to multiply the top by cosine. Because I got to balance things out, right? Whatever I do to the denominator to create my new denominator, I need to do the same thing to my numerator. Okay? So sine times cosine gives me sine x cosine x, so therefore I need to do the same thing here. Cosine times cosine gives me cosine squared x.
Difference between cosine squared x and cosine x squared.
No, yes and no. So cosine of x times cosine of x is the same thing as cosine of x squared, which is the same thing as cosine squared x. These mean the same thing. We write it this way typically so that we don't have to use parentheses. However, that's not the same thing as cosine of x squared. Okay, do we see that distinction there? Because that squared is just next to the x, that means you're only squaring the x, but it's not touching the whole trig function. The squared there indicates the whole trig function is squared, but you can also write it with parentheses as well. Okay, so now that I have common denominators, I can merge together. Okay, are we good from here to here? Questions so far? Okay, so now it seems like we're done, right? But there's actually something that we can do. Obviously, we can't cancel cosines out because there's a minus sign. But there's something that we can do with this. And the hint is there's a Pythagorean identity that we can do. So the Pythagorean identity that's related to this is what? Sine squared plus cosine squared equals 1. So what's the same thing as 1 minus cosine squared x? Yes, because if I subtract cosine squared from both sides, I can say that sine squared is the same as 1 minus cosine squared x. So how does that help us out? If I replace sine squared x in for the numerator, then that gives me even more opportunities to cancel out, reduce, and get it down to an even simpler expression. So you're going to see that this unit is going to feel like a puzzle. It's going to feel like, oh, there's a lot of things that you could do, but some things that you do may lead you to a dead end, and you have to kind of backtrack and try something else to kind of piece this puzzle together or try to get things to line up. Yes.
Okay.
So now I have sine squared x over sine x over cosine x. What's sine squared x the same thing as? What does that mean, sine squared x? Sine squared x, that square, well, first of all, what does that squared mean? Yeah, so what if I do this? What if I just do sine x times sine x so I can see all the individual pieces? Okay, what's nice and what's obvious here? What can we do?
Divide.
Take one of the signs out, and we're just left with what? Which is the same thing as tangent x. So we can get it all the way down to tangent of x. Okay, here's another something that we can do in terms of cleaning up. If you see common factors, sometimes that can help accelerate our steps towards cleanup. So here I have two terms. They both share what? They both share tan x, which means I can factor. Maybe sometimes factoring is the way to go. So I can factor a tangent of x out, which really means I'm really dividing the tangent out. So you think of it as dividing by tangent x from both terms. And whatever is left over will go inside the parentheses. So if I divide, or if I take out a tangent of x from the first expression, what's left? If I divide out a tangent x, what's left? A 1. Okay, so that you gotta be careful about that, because I think the tendency is, if you think of it in terms of, oh, I'm taking the tangent out, so I don't need anything anymore, but there's a placeholder, okay? Because I need to be able to redistribute and get back to my starting point. Okay? If I left that one out, then I'm creating a different expression. Okay. So I have tangent of x times cosecant squared x minus 1. There's something that we can do with this. You recognize potentially? Yeah, it's one of the identities, right? It's one of the identities. So the identity that's related to this one is 1 plus cotangent squared equals cosecant squared. So how can I rearrange this? Cosecant squared x minus 1 is the same thing as what? Right, so if I subtract 1 from both sides, I can see that, oh, I can make a substitution, replace cosecant squared x minus 1 equal to cotangent squared x. So now I'm left with tangent of x times cotangent squared of x. We can continue cleaning up here, but the nice thing is that tangent and cotangent are what? They're reciprocals, so that should help things out. But if you want to write it this way, you can. You can maybe write cotangent in terms of tangent, right? So cotangent squared is the same thing as 1 over tangent squared. Right? We know that cotangent is a reciprocal of tangent. Cotangent, yeah. But it's nice to have everything as apples to apples, because now we can see what we can do, right? We can remove one of the tangents from the top and bottom, and that's going to leave you with what? 1 over tangent, which is the same thing as right, but what's a cleaner version of cotangent? Yeah. Because we know 1 over tangent is cotangent. So we're just trying to get our expression as simplified, as reduced, as condensed as possible. Yeah, question.
The most simplified version doesn't have to be in sine and cosine. It's only for when you're trying to simplify.
Yeah, so usually if I'm starting off a problem, I like to get everything to the sine and cosine just to kind of see where the pieces are matching. But then once I get it cleaned up, I want things to be as reduced as possible. Yeah.
Tangent x 1 over tangent squared x 2 1 over.
Got it. So so tangent of x times 1 over tangent squared x, same thing as 1 over tangent of x times tangent of x. So if I can kind of put everything in their numerator denominator places, what do you notice? I can take out one of the tangents, right? And if I take out one of the tangents, then I'm left with 1 over tangent, which is cotangent. Okay.
Like
Yeah.
memorizing.
Huh?
So a lot of this is like memorizing stuff.
I wouldn't say memorizing. I would say more like you have a series of strategies, and you just try which one could help you get there, right? I mean, yes, it's memorizing, but I think we kind of already know these, right? And then if you know this one, which I guess technically you have to memorize, then you can arrive at these two without having to memorize it. Yeah, so I don't think it's as much memorizing as it is just trying different things and seeing what sticks. Okay, another strategy is sometimes it's helpful to distribute, right? Sometimes if you expand things out, you're able to see how the pieces can fit together a little better. So when I see parentheses, I'm thinking, okay, what if I just combine like terms and get the parentheses out of the way and combine like terms and see where that leads me. So if I FOIL this out here. Secant times secant is secant squared. Minus secant x plus secant x minus 1. Okay. What happens when you see like terms here? You see like terms? And we're just left with? Yes. Secant squared x minus 1. And if you look at one of your identities here, we do have an identity, which is 1 plus tangent squared equals secant squared x. And if I rearrange this, I can represent secant squared x minus 1, the same thing as tangent squared x. All right, another one is looking at a fraction and seeing, wait, is there a complex fraction going on? Secant and tangent doesn't look like something that can cancel out. So my initial strategy is let's just get them to be this trig functions that can be matched. So I know I can always rewrite my trig functions as sine and cosine. So secant can be written as what? All over. And then tangent can be written as sine over cosine. Okay, so I have a fraction over a fraction, which is messy, but I can always flip that denominator to make it come up, right? Dividing by a fraction is the same thing as multiplying by the reciprocal. So if I can identify the reciprocal at the bottom, I can bring that up to the top. The reciprocal at the bottom will just nicely go away because they got moved up to the top. And I'm just left with 1 times cosine of x divided by cosine of x times sine of x. And if I'm just multiplying these two fractions, what will go away nicely for us? Cosine, right? Numerator, denominator above each other that are being divided can just cancel out. So we're left with just 1 over sine, which is cosecant. Okay, let's just spend the next 5 minutes just working through some of these practice, and whatever we don't finish, we can pick up tomorrow. Okay. Is everybody good with this page? Good. Yes. Yes, you do. But really, I think the only thing you really have to memorize is this one.
Yeah.
Because everything else, you can build it or you already kind of know.
Figure it out.
Yeah, I think you already know what I'm for. Okay, let's look at page 4, guys. 5 minutes here. So let me let me write the identities up here so we can have easy access to it. Okay, so secant squared x minus 1, what can that be reduced to be here? Tangent squared x, okay. So that matches with letter P. Okay, 1 over sine x, that should be easy. Sine times cotangent. What can we do to make it a little bit easier to combine here?
Rewrite.
Yeah, rewrite cotangent. Anything match up nicely for us here? Sine. Okay, sine squared over 1 plus cosine x. There's nothing for us to rewrite in terms of sine and cosine. Everything's already in terms of sine and cosine. So let's maybe consider some identities, right? Is there something that we can do with that sine squared? What can I replace? What's equal to sine squared? Yeah, 1 minus cosine squared, right? Yes, sine times sine, but we know that sine and cosine is still going to be left unsimplified. But what if I can get it in terms of cosine? Then at least I can get my numerator and denominator to be matching in terms of the trace function. Now, you may not remember this. 1 minus cosine squared x can actually be factored. You guys remember a squared minus b squared? This is the difference of squares here. So I'm going to have to review some factoring here. If I have two perfect squares with a minus in between, I can break it down into its square root parts. And then a minus b times a plus b. The order of the sign is not going to matter, right? So if I have 1 minus cosine squared x, I can apply it in the same way because 1 is a perfect square. Cosine squared x is also a perfect square. It can be broken down into cosine x and cosine x. So what would that look like, difference of squares? Yeah. Yeah. And two perfect squares with a minus in between. We can break them down into their square root parts and put them in separate parentheses. So how can that help us out here? Yeah, we can take out one of the 1 plus cosine x. And we're just left with 1 minus cosine x, which is w. Okay, let's do one more and we can stop, okay? 1 plus tangent squared x. Do you recognize 1 plus tangent squared x? All right, so we'll try to do some more practice tomorrow, and then we can also start 4.02 tomorrow as well. Okay, come get your phones.
I see you.
Yeah.
What?
Yeah.
You get your first, so like, hey, we're not.
Well,
Yeah, good, we're trying. Like, it's not better.
Here.
Yeah.
Yeah.
I gotta say,
Fried rice. It's a little awkward because if they ask. Just not my last.
So we need to wait till like.
I ran out of.